Hello, everyone. In this section, which is a part 3 of Sn1 and Sn2, we will talk about the structure of Rx, which is a haloalkane. So, moving towards the discussion of the Rx and how this Rx is influencing factor to decide that either that nucleophilic substitution reaction is pursuing the Sn1 mechanism or Sn2 mechanism. So, or this discussion is about structure of haloalkane. So, when we say that we are going to talk about the haloalkane, so the very much important thing in the structure of the haloalkane is the alkyl group or the R group. And as we have seen that the haloalkane is basically having the R, which is bonded with one of the halogen one. So, what was happening with the alkyl of the haloalkane is, so let me draw this. So this is the general structure of a haloalkane. So we have discussed this halogen as a leaving group. We already have covered that in a section. And now our concern is to talk about this R group, because now we'll talk that how this R group is um, influencing and how its structure is basically determining that either that reaction is going through the Sn1 mechanism or Sn2 mechanism. So generally what we have infer or what we have concluded from our so far discussion on an Sn1 and Sn2 mechanism or nucleophilic substitution reactions in general. So the rate of Sn1 reactions are governed mainly by electronic factors. Electronic factors means there is a production of the carbocation and what is the stability of that charges. So this carbocation, which is positively charged. So the stability of that charges is basically the electronic factor. While the rates of Sn2 reactions, which is a dimolecular, a single step reaction. So on the other hand, this is governed mainly by a steric factor. So steric factor is basically which involve the steric hindrance. And the steric hindrance is basically the ability of groups, and these groups are basically the atoms, group of atoms, the functional groups, because of their size to hinder access to a reaction site within a molecule is called a steric hindrance. So if the entry point or the window or the site of the reaction from where that nucleophile has to attack on this haloalkane, so if that is hindered or that has been covered or secure or uh, they have been scored by some of the groups, so then this is called the steric hindrance. And now we will see one by one, firstly Sn1 consideration and then Sn2 considerations, that how these electronic factors and these steric factors really matters and how they influence Sn1 and Sn2 reactions. So firstly, Sn1 consideration. The first thing which we already have established, the Sn1 is basically the reaction which will proceed to the stable intermediate, and that is the carbocation formation. Now we also have go through that tertiary carbocation are the most stable. They have the lowest activation energy for their formation due to the hyperconjugation, whereas primary carbocation are the least stable because they have the highest activation energy of their formation. So they are rarely they form in a solution. So basically, they are such unstable that they are even we can say literally or on the practically. So they don't form as a carbocation because they don't exist in the system. So therefore, tertiary haloalkanes are most likely to react by carbocation formation Means if we have the tertiary haloalkane, so this can easily convert it into the stable carbocation formation, and that will proceed through the SN1 reaction. So here, this is the comparison, and you can see the three kinds of carbocation. So this is the primary carbocation, which has been formed through one of the haloalkane. And let's say if you just imagine there was a bromine, so that was ethyl bromide. So this has been formed from the one of the primary haloalkane. This was the secondary haloalkane. So that is a secondary carbocation which has formed by the removal of the halogen from this carbon. Now the tertiary one is where this carbon was having the halogen, and by the removal of that halogen, this has easily converted into the carbocation. And what's we said already, that the carbocation formation of the tertiary carbocation is more convenient, it is more easier as compared to the secondary and the primary one, because it has the least activation energy. So this really need very little effort to form a stable carbocation. So that's why we have the tertiary carbocation. If we have tertiary haloalkane, and they can easily convert, and they will go through the SN1 mechanism. Now, that was the previous slide, is basically giving you the idea about the alkyl carbocations. Now, there is another important type of carbocations we do form. These are called allylic carbocation. So, what allylic is? Any carbon which is next to a carbon double bond is basically allylic. So once a carbocation is formed, which is just forming, and it is next to this allylic one, it has this allylic functionality. So this will call allylic carbocation, right? So allylic carbocation, like allylic radicals, have a double bond next to the electron deficient carbon. The allyl cation is the simplest allylic carbocation. So basically, this is having the structure of this by the movement of this pi bond. So here you can see that we can say, so we wanted to see that how this allylic is basically influencing in the stabilization of this carbocation. So here you can see that this is the pi bond, and they can easily move from this pi bond can move or delocalize to the other side. And here that will be able to stabilize, and there will be the carbocation which will be formed. So let me pick this color. So here again, if that happened with this way in there, these pi electrons are moving back to this side. So then again, you will have this kind of formation. So it means they are the two equivalent contributing structure. So generally, what we know about the chemistry and their structure is that as many as the contributing structures we have. For example, the benzene has more than two contributing structures. So this is stabilizing the structure of that molecule. So that's why this allylic, because of this pi electron delocalization, is stabilizing this positive charge. So this allylic cation or the carbocation is again the stable one. So now we will see another kind of allylic cation. But firstly, I just wanted to mention that in a previous slide, I did I've shown you the one of the primary allyl cation or allylic carbocation. This is a primary one. And now we can see the example of the secondary allylic cation, where this allylic carbocation, this carbon is just next to the doubly bonded carbon. This is allylic one. Now, this allylic carbocation is a secondary because it's again interacted or in a bond with another R group. And similarly, we have the tertiary allylic cation. Now, another important carbocation is the benzylic carbocation. So benzylic carbocation is in which a carbon attached to a benzene ring bears the positive charge. These carbocations show same stability as allylic carbocations. Both are stabilized by resonance delocalization of positive charge due to adjacent pi bonds. It can be written as C6H5. This is the condensed formula of this benzylic carbocation. So this ring of the benzene we can write together as C6H5 to give you the phenyl group. And then this is a CH2 because this is aliphatic, this is outer of the ring. So we are writing this separately, and the positive charge is to mention the carbocation. Now you can see, as I've told you, that there are more than two contributing structures. So they are again stabilizing. So here you can see this is the pi electron, and it can move there. So there will be the double bond and the positive charge will come there. Then this keep on going unless we again return to the original structure, right? So it means the pi electron availability, because they keep on delocalization, so there is no harm that only the one position is facing that one. So this is stabilizing the molecule. So the benzylic carbocations are equally stable as the allylic carbocation. Now we will compare where the benzylic carbocation and the allylic carbocation stays um, along with the aliphatic or the allylic or the alkyl carbocation, and we'll see where they stand if we just compare these three cases of the carbocations. So these are the relative stabilities of the carbocation. The least stable, or in fact the carbocation, which say they are rarely formed. So this is a methyl, then the primary alkyl, then there is the secondary alkyl, primary allylic, and primary benzylic. So you just have to keep in your mind that the secondary alkyl carbocation is comparable to the stability of the primary allyl and the primary benzyl cation, right? And then the tertiary alkyl is equally stable as the secondary allylic and the secondary benzylic, and they are far stable as compared to these ones. Then the most stable case, most extreme of this carbocation stability is the tertiary allylic and the tertiary benzylic one. So this pink arrow is mentioning you that from where side we are moving towards increased stability of the carbocation. Thus, in summary, SN1 mechanism should be considered for allyl and benzylic haloalkanes because they will go for the stable carbocation formation. So definitely wherever there is a carbocation formation, stable carbocation formation, so they will opt the SN1 mechanism, even if they are the primary haloalkanes, right? Because the primary haloalkanes, if they are allylic and the benzylic one, right? So they are comparable to the secondary alkyl carbocation. And we know that the secondary alkyl carbocations or the secondary haloalkanes are in between, that from where they can switch to the SN1 or SN2 depending on what other factors are. What is the leaving core? What is the strength of the nucleophile? What is the solvent, etc. So that you have to keep in mind, that if the certain condition is given to you or you are dealing with allylic and benzylic haloalkanes, so you should have in mind that they will opt the SN1 mechanism. Now we'll go to the SN2 considerations. So as we discussed, that SN2 considerations are basically, or the SN2 mechanism is basically dependent on the steric hindrance if we consider the structure of the haloalkane. So in an SN2 mechanism, the nucleophile must approach the substitution center and begins to form a new covalent bond to it while the leaving group is departing. That is what the mechanism is. So compare the ease of approach to the substitution center of a primary haloalkane with that of a tertiary haloalkane. The approach is considerably easier for bromoethane than for tertiary butyl bromide. So I will show you in the next slide with a picture as well. So two hydrogen atoms and one alkyl group screen the backside of the substitution in case of the bromoethane, while there are the three alkyl group which screen or block the backside of the tertiary haloalkane. So here we can see that one, and that will um, make you more understandable for um, this concept that here, this is the bromoethane. This carbon is bonded with the small atoms, hydrogens, and then there is only the one big atom, that's a bromine, and there is the methyl one. So the bromine is a leaving group here. So from which side the nucleophile is attacking? It's on a back side, because in case of SN2, so this bond is not breaking as a first step, and there is no carbocation formation as such. So if we compare the primary one, so what is happening, the nucleophile can easily attack and access this site, and that SN2 mechanism can happen. While if we see the tertiary haloalkane, so this is too crowded side, and that was the only mean if it has to go through the SN2 mechanism, because in SN2 mechanism, nucleophile is approaching from the backside and bromine is leaving, because nucleophile cannot attack from the front, because there is already the bromine which is of the considerable size, and this is on the front side. So how it can then approach from the side? So it has to attack from the backside. But here in the tertiary case, this backside is already being crowded, it's cotton, and this has blocked with the three methyl group. And if you just compare the size of the methyl with the hydrogen, this is far much bigger. So this side is blocked, and this is the space filled diagram of this molecule, that how that do exist in the form of their volume. So here you can see this is a bromomethane, ethane ethyl bromide is a common name. So this is a free excess, it can easily work on it, while this is the blocked one, so there is no attack of the nucleophile from the backside. So this is not going to pursue the SN2 mechanism. So this is happy. Once it will cleave the bond with the bromine, it will be in a stable carbocation formation, and then it can easily go through the SN1 mechanism. Now the competition between electronic and steric factor. Here this picture will give you the idea that from which side you can say that this reaction is happening to the more chances and the priority for the SN2, while the other one has for the SN1. SN1 is basically governed by the electronic factors. So the carbocation stability is basically involve that if we have the um, strong positive charge stabilization on carbocation, so that will pursue the SN1 mechanism, and it moves from the secondary. It happens from the secondary if we are working on alkyl carbocation, right? So then there is a primary and the methyl one. So this is basically involved on the steric hindrance, and the ease of the site of reaction is from primary to the methyl. So the ease of site of reaction for the nucleophilic attack from the backside, NSN2 is increasing from tertiary to the methyl side, while the carbocation stability is increasing from methyl to the tertiary one. So that both things you have to keep in your mind, that is what is ease in a site of reaction and what is a carbocation stability. So the carbocation stability as a result will lead to the SN1, and ease access to the site of reaction for the nucleophile from the backside will go for the SN2 mechanism. So another factor which is very important is the branching at the beta carbon. Now, firstly, we should know that what the beta carbon is. So, the carbon with which this halogen is attached in the haloalkane, this is called alpha carbon, and the carbon next to that alpha carbon is a beta carbon. For the simple haloalkane, we have seen if the haloalkane is a secondary or the tertiary or the primary one, so they are moving towards the primary, secondary, or the tertiary carbocation. So we have seen that stability. Another factor is also important, but maybe your haloalkane is a primary one, but it do have some of the branches on the beta carbon, which is just next to that alpha carbon. So what is that impact and how that influence the SN2 mechanism, right? So this is another steric hindrance effect for the SN2 reaction. If there is an increase in the branches on the beta carbon, so that will reduce the rate of reaction, and that is not happening through, and that this is not likely to happen through the SN2 mechanism. So this is the alkyl bromide, and we will see there are the four examples of the alkyl bromide, right? This is the ethyl bromide, this is propyl, this is the isobutyl, and this is the neopentyl bromide, right? And here you can see the how many branches we are adding on the alkyl halide, and with each increase in the uh, beta carbon branch. So what is an impact on the rate of the reaction? So the ethyl bromide has been taken as a reference. So it has the beta branch 0, because on a beta carbon there is no further alkyl group. So there is 0 branch on it, and its rate of reaction was 1.0. Now we will compare the other cases relative to that one, that what is an impact on it. So here you can see this is the propyl bromide. So on the beta carbon, there is one branch, and the rate of reaction has reduced from 1 to 4.110 to power minus 1. Now, if we have increased that beta branch to 2, so this is 1.2 to power minus 3, and then if that has been happened with the 3, so here this was to 1.2 to power minus 5. So that's just too much reduction in the rate of reaction via the SN2 mechanism, the probability to opt the SN2 reaction. So it means that if we have the higher beta branches, so that will move from SN2 to SN1 mechanism. So they will more probably go to, and they would likely to go through the SN1 mechanism. And this diagram is for you to give you the idea that once we increase the branch, though this is a primary haloalkane, but from the beta carbon, this has overly crowded with these alkyl groups. So that's why now the nucleophile is not having that access for the backside to attack on it. So that was for today, and hope you get that idea how the structure of the haloalkane, and especially the alkyl of the haloalkane, do influence the SN1 and SN2 mechanism. So have a look on the further chapter examples, and if you have any questions, don't hesitate to ask. Thank you. Have a good day.